Okay, so my job today is to answer the question, why study fluid mechanics, and hopefully get you people interested and try to tell you that this is a worthwhile thing to study. Okay, so here's a question for you. How many of you like sports? Watching, playing, anything? Almost all hands. How many of you hate it? Nobody hates sports. Okay, name a sport in which fluid mechanics is not very important. Anybody? Do you know what fluid mechanics is? It's a flow of air, water, any liquid, any gaseous material. Yeah? Any thoughts? Can you name a sport where fluid mechanics is important? All sports.
Swimming or tennis, anyway.
Swimming, tennis, okay. Huh? What? Say loudly, I can't hear. What? Shuttle. Shuttle, are you saying it's important or unimportant? Important, okay. Where is it unimportant? Chess. Okay, so this morning I was hoping somebody will say chess, and I looked at the internet. It shows that a player, like these top players, when they play chess, then their blood starts flowing to funny parts of the brain where it otherwise doesn't flow, okay? So like they use parts of the brain which we guys normally don't use. So there's fluid mechanics there, blood flowing to their brain, okay? So I couldn't come up with an answer. Maybe there's some, I'm sure there's some dumb internet game we can play where fluid mechanics is not important. So like here are a few sports where it is important, and I just put this because I wanted to say that swimming costumes are designed in the NASA wind tunnel, and so like a lot of big business goes into the fluid mechanics of sport. Okay, so fluid mechanics is important for all length scales. How much is an angstrom? Wonderful. 10 minus 10 what? Meters, perfect. Light years? Yeah, it's some, 3.13 kilometers.
Yeah, 10 is to 50. 10 is to 50 meter or 10 is to 12.
Yeah, it's something like that. So fluid mechanics is important from this scale to this scale. So here's a nano droplet which has only some number of molecules in it, and we can't even think of it as a liquid drop because each molecule is distinct and it's walking on some surface. Even the surface is, crystalline. It doesn't look like a complete solid. And then you go a little up in scale, there's swimming bacteria who make this lovely pattern. It comes from an instability called bioconvection. I can tell you about these instabilities later on. But here I'm just trying to give you examples of fluid mechanical problems. And what I'm trying to impress upon you is that in each of these areas, lots of research is going on today, and it will go on for the time when you people become PhD students and later on. So these are all very interesting open problems to choose from. And then there's a lab on a chip. Here's a whole lab which is shrunk into some micrometers. And so like you can get your blood test and everything done much faster with smaller amounts of blood and less pain and so on. So there's a whole industry trying to build these lab on a chips. And then, of course, the lungs, we talked about blood flow, any musical instrument, a flame. Flight is a very important fluid mechanical problem at all scales. The hardest of these is bird flight, and second hardest is insect, and relatively easier is aircraft. Why is that? Don't know. You had a guess. It's because these guys flap their wings. These things are fixed wing, and flapping wing makes it much more complicated, the flow much more complicated. These guys flap their wings and they have very complicated wings with feathers and so on. So this is a very, very hard problem to understand. Basically, even to understand how it lifts itself is very hard. And then we're now talking about some bigger scales where, you know, how many of you have been to these caves? You've never been. What are these? Any guesses? Stalactites and stalagmites, you know what they are? Yeah, you can go and read about that. So it's basically limestone caves where, you know, drops of limestone come down and solidify in these very particular shapes, and you can actually write simple equations to calculate, you know, these sharp conical shapes. And these are stalactites, and on the floor there are stalagmites. And then if we want to understand pollution, this was a recent volcanic eruption. Anybody read about it? This is not Hawaii, it's in Kyushu. Maybe it was after the Hawaii. This was like a month ago, about 1 month ago. And look at the kind of particulate flow it is generating. It's a very, very big fluid flow that is generated. And so fluid dynamics is important in all of these situations. And all the way up in scale, I've you know, skipped over many things till merging galaxies. Okay, so we're talking a whole range of length scales. We're talking a whole range of people who will solve it, not just maths, but astronomers, engineers, biologists, all kinds of people are interested in fluid mechanical problems. Or put another way, fluid mechanicians can say something about many different kinds of areas. And so like one of my favorite areas is instabilities, and flow instabilities lead to patterns. We can talk about what causes these instabilities later, but in all of these you get some kind of nice length scales. This is a bunch of bubbles. This is dosa, and you can see it everywhere. So I've put here, whenever you see a pattern, next think of us. Think of our group who studies these things. And so typically what happens is that when you have, like here, the sand, if you have a completely uniform height of sand and you perturb it a little bit, it turns out that the completely uniform state is not stable. And by not stable, I mean like a pendulum, if it's hung this way with the weight at the bottom, it's stable, right? But if I hang it upside down, it's unstable. So any perturbation will make it come far away from its state. So in that sense, the flat sand is like an upside down pendulum. So you perturb it slightly and it will never go back to being flat. It will go back to showing these shapes, and it even forms sand dunes. So in each of these, there's communities of people who spend their lives working on this. So to understand these, so then it usually what happens is you're perturbing a thing, you perturb it with some random disturbance. You're not putting some beautiful disturbance like this, but each grain of sand knows whether it has to be up or down. So it arranges itself in a hill-like pattern. So this itself is a very interesting thing for instabilities. Have you done Fourier transforms? Yeah. So like usually one Fourier mode or one wavelength will get selected. And that's why you get this. So all wavelengths are unstable. I mean, a range of wavelengths can be unstable, but one of a few small range of wavelengths will be much more unstable than others. And because of that, that wavelength gets selected. Although you put in an arbitrary perturbation, the other wavelength components of that perturbation died down and this one survived. Okay. So I just want to make the point that fluid mechanics has, you know, given rise to some areas of mathematics, some research, quite a bit of research in mathematics and vice versa. So the area of fluid mechanics and mathematics are very deeply interconnected. So you would have all heard about chaos theory, right? In nonlinear systems. So chaos is one of those things where, you know, turbulent flows encourage people to think about chaos. Similarly, singular perturbation, we'll talk about singular perturbation a little later. So don't worry if you don't understand what it means. And similarly with computers, I don't know why I said computers give rise to fluid mechanics. Yeah, we need computers to give rise to solve things better, but also to solve the problem of turbulence and to solve the problem of weather and climate, computer scientists work very, very hard because today's computers cannot solve this problem. It cannot solve this problem exactly. And the prediction is that even for the next 100 years, we will not solve fluid flow exactly on however much computers become faster. So we have to develop good methods to study fluid mechanics. Yeah, so I wrote the word turbulence. What does the word mean to you? Unsteady? Any other thing? Jumping up and down in a flight, yes. When you get scared on a flight. Anything else? Have you seen turbulence every day in something? In what? You can't see tectonic plates every day. Where do you see turbulence every day? Turbulent flow of water. In your washing machine, if it has a glass door, you can see it. Yes. Yes. In fact, like I'm holding my hand like this, right? If I do this to my hand, and if you had a, Schlieren camera or something, you could see the vapor going up. Because my hand is warmer than the surroundings. My hand is at some 98 degrees, which is 37 degrees. And this room is kept at 25 or something. So there'll be hot air which will rise. So around me, you can see a nice plume if you could see it. So yeah, so turbulence is everywhere. Sometimes you can't see it, that's all. So then, so we need to study it because at all length scales, we have to worry about it. In all situations, we have to worry about it. So for us, like, let's just give a simple, this is like my take on turbulence. There's different people describe turbulence differently, but you can think of a bowl of pasta, long pasta, and these pasta are not of the same radius. Some are thinner than others, and some are pretty fat, and and they're all interconnected. But the beauty is that they're all not sitting still. These are called vortices, where you have a curl of a velocity vector. If you've not studied curl, you'll study about it. How many of you know what a curl is? Quite a few of you. But don't worry if you don't know about it. This is called the curl of the velocity vector. All that we need to worry about is that here is this pasta. It's spinning round and round. Okay, like a tornado. So each pasta is spinning round and round. And because it's spinning, it's doing things to the other pastas. It's telling them where to go. So each one is obeying the other pastas and it's giving orders to the other pastas. And there are stronger guys who give bigger orders than the lesser guys. So they keep pushing each other around. And then they're also doing lots of other gadbad, like they keep merging, they join with each other, they stretch a lot and become more powerfully spinning. They reconnect, like some of them will cut there and connect with someone else. So like it's a big, very complicated bowl of vorticity, which is happening everywhere. Like in your washing machine, you can't see each vortex, but it's happening there. It's happening when I do this to my hand, everywhere, okay? So this is a complicated problem. If I want to predict it, I cannot. It's obviously a chaotic flow, but I can predict some things about it. I can predict average quantities. I can't predict where the velocity or something at each point, but I can predict many things like on an average. Is that okay? Okay. So the other property of turbulence is that it mixes. So here they've done this simulation and they pulled out vorticity of a certain size in a random turbulence. And you can see that there are these pasta level things. They're not very clear to see because of the way they're drawn, but many of them are a lot longer than you see here. So these are isosurfaces of constant vorticity. So we normally think of turbulence as mixing. So I'll come back to this point, like when we put sugar in our tea, we start mixing it because we want every part of the tea to become sweet, not just the bottom, okay? So we think of turbulence as something which mixes, okay? Now, I've written down some of the equations we use in fluid mechanics. These are true for a range of things, but they're not true for a range of other things. So for example, if I'm talking about a re-entry vehicle coming back from space into the Earth's atmosphere, then I cannot use these equations because the gas is very rarefied there, and like the re-entry vehicle will see one molecule here and one molecule there. The gas will not be full of molecules. There'll be a big mean free path. So these equations will not be valid in those things. In that nano drop I showed you, these equations will not be valid. There's a variety of situations where they will not be valid. Even in supersonic flight, mass balance will not look like del dot U equal to 0. So don't worry if you don't understand the form of these equations. I'm just giving one example of mass balance. This is correct for incompressible flow. This is correct for, let's say, the flow of water in a swimming pool. Okay, so that is mass balance. Momentum balance. Who's heard the word Navier-Stokes equations? Hands up higher, please. Okay, great. So Navier-Stokes equations are just the momentum balance. Like you can think of it as Newton's laws for a fluid. Okay, so we know that force is equal to mass into acceleration. So then, like, this is actually the acceleration. I've written acceleration, this term is the acceleration equal to force divided by mass. That's what I've written here. And this is the pressure force, this is the viscous force. This quantity nu stands for the viscosity for us. So viscosity is a thing which gives friction in the fluid and it slows down the fluid. So just as a thumb rule, honey is very viscous and air is less viscous. Okay? So then there is energy balance. So in order to understand any of these things, we'll write down all of these equations, but very often we cannot solve these equations. So for our particular flow, we'll try to derive simpler versions of the Navier-Stokes, derive things which may be analytically solvable. And when we are lucky, we can solve some of them analytically. And we also try to bring it down to a point where our system, if we cannot solve it analytically, we can solve it computationally. And not everything, as I told you, can be solved computationally. And that's because the whole thing is so nonlinear and chaotic. It's often impossible to solve either analytically or numerically because the range of scales is too much for computers. So what I mean by that is the following. So I've shown you a jet, right? Now in that jet, suppose my Navier-Stokes equation contains terms like dou U by dou X. Right? Or dou V by dou X, something like that, dou U by dou Y, things like that. So like suppose I have 2 points here and U, and I want to calculate the delta U. Then I can Taylor expand this, right? And I can write it in terms of U of Y plus 1 is equal to U of Y plus blah, 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 in terms of many derivatives. So I can actually compute the next situation's velocity by knowing this. But the problem is that, there are vortices of all scales. There are very, very, very tiny vortices and there are big vortices. Both of them exist in turbulence. So then, like, if I want to write the derivative correctly, I need to have a very large number of grid points. And then I have to numerically write it down. And that amount of large number of grid points is impossible for any computer. So then we have to play tricks. There's many tricks which I can't describe now in order to solve these things approximately. And in some of those situations, those approximations go very, very bad, like in the monsoon prediction. So we have a big group here who tries to understand the Indian monsoon, and we'll be very, very happy for people to join us and work in this project. And it's going to take years to really understand, let alone predict. And the reasons are that there's no way on earth, like even for this jet, it's very, very difficult to solve it on a computer. Forget something on a planetary scale. That is the point. Okay, so we'll come to singular perturbation. I chose 2 examples which come in maths, which we have used often in our work. And when we do our work, we've often seen this thing happen again and again. And in the Navier-Stokes equations. And I've just not written a differential equation here. I wrote like a algebraic equation so that I can convey the central idea, but the idea is the same in Navier-Stokes. Okay, so I'll come to what we do in Navier-Stokes. But here is a second order equation. Whatever, quadratic equation. What's the solutions for this? 2 and 1 are the solutions. So x equal to 2 and x equal to 1 are my two solutions for this thing. Okay, now I could take my quadratic equation and change it ever so slightly. Instead of -3, I put -3.0000. I could put any number of zeros and 1. Okay, what did I get as a result? Instead of 2 and 1, I got two x's which are very close to 2 and 1. Agreed? So this kind of perturbation is called a regular perturbation. Okay, so what I mean by regular perturbation is that if I look at this equation, I'll say, yeah, like let's throw all those things. Let's call it 3 and work with it, and life will be good. So we'll call it 3 and work with it, and I'll get nearly the correct answer. And then if you tell me, no, like I'm not happy with what you did, I wanted the answer correct to 6 decimal places, then I can say, okay, I will now expand this and I'll make an equation for the first correction to it. And I can use the 2 and 1 and expand about it and get the corrections. So there's a standard list of a protocol I can follow to get you the answer to whatever decimal place you like. Besides which, this is a quadratic, so I can solve it exactly. Agreed, everybody? So we'll go on. Now, what is the difference between this perturbation and this perturbation? So first term, I've added something in the first term. I've made it a cubic rather than a quadratic. I didn't perturb something which was already existing. So what's the problem with that? Any problem you see? Yes? X is my only variable, Baba. Very good. So what will be the difference? Perfect. Perfect. So like if I throw this away, I'll get only 2 roots. So I'm missing something important that this equation can do. I'm missing something very crucial. In other words, the third root. So like I did this by hand, I could be wrong. So I've got like approximately 1, approximately 2 and minus some big number. I think this is correct, like you can correct me. But you can actually see that there is a new solution of x, which I'll completely miss if I just say, yeah, throw this away. Okay, so in fluid mechanics, this happens again and again and again and again. It's called boundary layer theory. It's called the boundary layer approximation. So when you go towards one part of x, so like typically if I think of x as my flow domain, then wherever x is small, I'm okay. But wherever x is big, I'm terribly bad. I'm getting a terribly wrong answer. So like this is the kind of thing which happens in the Navier-Stokes equations. And the reason for that singular perturbation is the viscosity term. It's this term. So typically this term is very, very small, like in an aircraft or in the micro flows, this term is very big. But in the bigger flows, this term is very small. And you can immediately see, like if I say, oh, it's so very small, so let me throw it away, then I'm reducing it from a second order to first order. So I'm in deep trouble by throwing it away. So this kind of thing happens again and again, and this little thing called viscosity, which everybody believes is unimportant whenever the flow is very large, can become extremely important in some regions or in some situations. So I can't always throw this away. So in fluid mech, in high Reynolds number flows, that's what this is called, there is singular perturbations everywhere. So like here is a solution where there's flow past a cylinder. So I've kept a cylinder and there's flow going past. And in theory, if there was no viscosity, this is what the streamlines will look like. They'll just bend a little bit and go back. And this side and that side will be perfectly symmetrical. And whereas the real flow looks like this, it's called D'Alembert's paradox. So this is actually, any guesses what this is? Huh? Yeah, these are vortices, very good. What is this thing? That's the object. It's actually like something which approximates is approximately a cylinder, but it's actually an island. It's an island, and this is an aerial picture of the clouds. Okay, so the island was still here. The clouds are there. But the vortices that are formed stay all the way into the atmosphere. That's interesting, right? It's called the von Karman vortex treat. And so this is for vanishing viscosity. This is for zero viscosity. And this is what we mean by a singular perturbation. This answer has nothing to do with that answer. You get everything wrong if you go with zero viscosity. Okay, is this point coming clear? You want me to repeat it? No? Great. Okay, so this is basically what I wanted to tell you there. There's one more interesting thing mathematically which comes again and again in stability analysis. Let's talk about that. It's called transient growth. So, has everybody seen equations like this? Yes? So here is an example with two equations. And I can solve this exactly, right? And my solution is x1 is e to the minus t, that you can see directly. And x2 is e to the minus something plus e to the minus something. So tell me, like, and I've called it linearly stable. Because what I've said is x1 and x2 are perturbations about some point. Like I've gone back to my pendulum, I've perturbed it by x1, x2. And then I'm asking, is x1, x2 going to die down or is it going to blow up? So e to the minus something, e to the minus something means what? Stable, right? Agreed? It's going to die down. So at time equal to large, what will x1 and x2 be? 0. So both of them are going to die down to 0. Okay, so now you think, oh, there's no fun in this. This is a linearly stable system, like nothing at all to worry about. Wait, in fluid mechanics, whenever there is shear, like there's always velocities which are changing from one place to another. You will get fooled if you think this is stable. Lots of funny things will happen in fluid mechanics and I'll tell you why. I've now expanded the x2. x2 equal to x2 0 plus blah blah blah. I've Taylor expanded, right? E to the t. That's what I've done. And now depending on your x2 0, at very small time, I can throw away those terms, right? At very small time, I can neglect t square t cube and all. Agreed? Agreed. Then I have x2 naught plus t times something. So actually I have x2 growing in time. Do you see that? So at small time I can have x2 growing in time. Although at very large time it is going to decay. Okay, but this temporary growth or transient growth can take you somewhere else. Can take you to turbulence when you think your flow is not turbulent. It can change the state of the system. So it can, it can be very, very important. So we call this system, let's go back there, oops. So this thing is actually called an eigenvalue problem. Because only for certain values of this thing, only certain eigenvalues you will get x1 and x2 to be non-trivial. Otherwise 0 is always a solution. So I can construct a matrix out of this and I'll have certain eigen directions, certain eigen vectors along which I can get a non-trivial solution. Okay? So if you don't know this, it's going to be covered in next week, right Siva? You'll start getting an idea of what eigenvalues are in the next week. And then you can try to solve this or talk about it. So it actually is not important to you right now because I've shown you a nice photo which explains it. You don't have to understand what it is. So like here there is two black lines. This is x1 and this is x2 at time equal to 0. So I just have two things, okay? Two vectors in this direction, in these two directions. What's the resultant? It's that little black line. Agree everybody? So that's the resultant. And now after time t, both of them have decayed. x1 shrunk till here, x2 shrunk till here. Both of them have decayed. But what happened to the resultant? It grew, right? It grew. So I just took it there to show you the projection that it grew. So like you can try this out for yourself. Like just take two vectors which are not orthogonal. If they were orthogonal, you'll get no growth. Take them non-orthogonal and try this out for yourself. and you will see that there is disturbance growth, x1 and x2 ka growth. Now this is in a 2D system. In fluid mechanics, we are working with infinite dimensions. And we've got velocity, temperature, salinity, moisture, radiation, so many things happening all at once. So this system can be furiously what we call non-normal. This matrix is not self-adjoint. So although the eigenvalues minus lambda 1 and minus lambda 2 are both negative, lambda 1 and lambda 2 are greater than 0. This thing can give transient growth. And in fluid mechanics, you can get enormous levels of transient growth. And what happens because of that is instead of just monotonically decaying from 1 to 0, it goes up. It can go up by many, decades. This disturbance grows up. And by the time it goes up, it forgets to be linear. Remember that this is a system. In the Navier-Stokes, it's a nonlinear system. So whenever I put a small perturbation, I'm saying, okay, let's imagine Navier-Stokes looks like this. dx by dt is minus ax plus bx cube. Okay, so now in this linear system, it's all dying. But what happens is when x has grown very, very big, sorry, I should have called this x, not y. When x has grown very, very big, then this term can also become important. So this approximation that I made by throwing away the cubic term was not good. And then it can go to a new state. So instead of dying down, it goes up to turbulence or some other state. So this kind of thing happens again and again, and we use it in our work. Okay? So Sharad Jose, my student, he has looked at, channel flows. Like now when you switch on a motor and you're asking, from your what do you call that, sump, you want the water to go to your overhead tank. The flow in the pipe is turbulent. There are vortices, there are all kinds of things which you cannot see. So this is just a channel version of that. And this is what the vorticity looks like in your average pipe. And we've shown that those things which we thought were unimportant, two things which we thought were unimportant. One is the viscosity and its variation because this channel is cold above and hot below. That makes a huge difference to the way the turbulence is. It can even kill the turbulence or it can increase the turbulence. So the other thing I told you is this transient growth. All this turbulence is happening in a place which should not be turbulent. It is supposed to be laminar, but because of this transient growth, although all the eigenvalues are negative in the system, it's gone off to some other state. It's gone off unstable. Okay? So the cloud is a very important problem, and here is, I told you we guys study the Indian monsoon. So we should, so just stare at this thing. It's cloud cover on the world. And this movie is from NASA MODIS. And so I'll play this movie, focus on India. Do you all see India there? And I want you to tell me what you saw about India. If I click it, will it play? Whoops. How do I make it play? I'll go there and try. Okay, keep watching India. This is over 8 years, okay? The cloud cover over 8 years. A lot of the world is under cloud cover. It seems to be, movie finished. Any thoughts? You want to see it again? It's repetitive. What happens? Covered and uncovered. Did everybody see that? So the cloud goes like this, back, like this, back. And when it's covered, we get the monsoon, right? So that's basically what we're seeing. So the whole world is 70% cloud all the time, but India is very special. It becomes super cloudy and then no. By the way, there are 9 things in the world which are called monsoon. And most of those other monsoons are pathetic compared to the Indian monsoon. In fact, the Indian monsoon is seriously big. It's the biggest, one of the biggest weather events. And we don't understand it at all. We don't, I mean, here you can see the cloud cover going like that. But at the same latitude, like Arabia and Sahara, all of those guys are sunny, sunny, sunny. So something very bizarre is happening here. The bay is very important in this equation. It's important for us to understand clouds, and it's important for us to understand this very complicated dynamical system which is happening on a rotating Earth. And so the Earth's rotation also plays a very important role. So this is what it is. So I've now put about a single cloud. There's turbulence in a single cloud. It pushes around aerosol particles, small dust or pollution or any sea salt, any particles in itself, inside a cloud. Now I'm imagining that we're sitting inside a cloud, okay, single cloud. There's aerosol particles. Those raindrops condense on those aerosol particles and they become bigger and bigger. This cloud flow is a most complicated form of turbulence, one of the most, because normally what happens is, like suppose you think of the ocean and let's say you're thinking of some bacteria or something living in the ocean, okay? So like the ocean waves, you know, massively, push around the bacteria. Do you expect the bacterium to do anything back to the ocean? Yes, no, maybe? Louder. Do you expect that if I double the number of bacteria in the ocean will have a problem with it? Or the waves will change? No. Everybody agrees with the no? Yeah. The beauty is clouds are different. There are these aerosol particles which are micron big. And these guys are feeding back into the turbulence. So you think like these guys should be the slaves who just get pushed around. But they can be the guys who decide about clouds' lifetime and everything. Because they make raindrops. When this condensation process takes place, latent heat is given out. And because of latent heat, that part of the cloud becomes lighter. And then it climbs up because it's lighter compared to its surroundings. And this upward climbing actually like messes up the turbulence to a great degree. So cloud flows are a very, very interesting problem. We'll talk about this in break. So there's many, many open questions. And most of the things I've shown you, there are many PhDs to be done. As in many PhDs to be done. So I'm just naming one open question in this, which is how does a cloud drop become a raindrop? So by the diffusion equation, if A is the raindrop radius, A dA by dt is some kind of constant. Okay, and I can solve for that to get A goes as something root T. And the time it will take for this little particle to grow into a millimeter raindrop is too slow. A cloud lives for a few hours. And this is going to take days to become a raindrop. So this we don't understand how raindrops become big so fast. Actually, they go from 10 micron to 1 millimeter in 10 minutes. And this is an open problem. So yeah, so basically formation to 10 micron is 3 seconds. 10 micron to 1 millimeter is 3 days. So this cannot happen. Droplets are growing too fast in real life, and this is called the droplet growth bottleneck. So one thing that people have been suggesting is that turbulence is the answer to the droplet growth bottleneck, but this is not settled. Like even last month, there was a paper strongly disputing it, and there's like almost two armies on either side. One saying that turbulence is important, and one saying that turbulence is unimportant. Okay, and they keep shooting papers at each other, and also questions in conferences. Okay, so I won't go into these things, but various things happen due to turbulence. Basically, droplets can come closer together, or what is the thing? So we go back to the McSee, and we said turbulence uniformizes everything like sugar in my tea and so on, right? Okay, but look at these simulations of my colleague Shamridji. The yellow color are vortices in the turbulence. It's just a 2D turbulence. These black dots are droplets, which are just exaggerated terribly in size just to make you see them. What happened to the droplets? Louder, Baba. Today morning, Siva told you, no, louder. What's happening? They're not uniform, it's doing the ulta, right? We started out with uniformly spread, agree? And then turbulence is pushing them into funny corners. So is this intuitive or counterintuitive? Yeah, so that is basically what they're doing, what turbulence is doing to droplets. And this is happening because droplets have inertia. And so like they get centrifuged out of the vortices. And so they're collecting in regions where there's very little vorticity. You get that? And now like these droplets have better chances of touching each other and joining together to grow fast. So the question is this enough? We have not solved that problem, but we solved this very messy equations. The Navier-Stokes is given in that. The first two terms are Navier-Stokes. All other things come because there is phase change, there is water vapor, temperature, liquid water, yevo. So we'll not go into all that. But the summary is that we show that plane flow looks like this and cloud flow looks like this. So this may not excite you guys very much because there's two kinds of vortices there, but it excites turbulence people because you get a lot of these very small scales which actually lead to early death of turbulence or early death of the cloud. And these extra vortices are formed because of what I told you, because these droplets went to funny areas, then phase change occurred only where the droplets were. So temperature was inhomogeneous in the cloud, and so there were buoyancy effects. And every time one place is hotter than another place, you get baroclinic torque. You get production of torque, which means production of these small scales and intensification of all the vortices. This is the kind of work we do. Ritabrat Thakur works on turbulence in the bay, which I don't have time to tell you about. And here is a movie from Sumit Birwa. I think he's somewhere there. Yeah, he's right at the end. Yeah. So here is a ball which is just falling in a viscous fluid. Okay, and we ask the question, does it touch the floor? So I'm just giving you different examples of the kind of problems we can solve with fluid mechanics, right? So here's a ball, it's going through this viscous medium and it's touching, it's touching or not touching the floor. That was a question. So Sumit recently showed, and his paper came this month or something like that, that this thing actually does touch the floor, although like the theory, it's called shallow water theory, says it should never touch the floor, at least not in finite time. It says that the pressure will build up so much, the pressure in this viscous fluid will build up so much that it will resist the ball coming down. So by making electrical contact, he showed that it's actually touching. But here we actually, try to write down the equations in a better way compared to shallow water theory or lubrication theory. So we try to write the equations in a better way, and we got this complicated equation, which is again by a boundary layer approximation. I told you what a boundary layer is, right? The singular perturbation stuff. So we did that and we got a new equation. So this is just an example of an equation you can derive from the Navier-Stokes, and then it's in a much easier form and you can actually solve it. And then we can get solutions. I don't have the complete answer yet. We've solved this, but I can't tell you the physics yet. I'll tell you next time we meet. And so before I end, I want to thank all my ex-PhD students. Most of them are faculty members in various IITs. And I want to acknowledge all the present students who are doing a lot of very interesting work, and I didn't have time to talk about each one's work. Priyanka is over there, she is a postdoc, and Jason is a postdoc. So they are the senior most people in this group, and I didn't have pictures of some of these, or I didn't have time to find the pictures. So my conclusion is that fluid mechanics can be empowering. If you do fluid mechanics, you can answer a range of questions from a very small scale to a very large scale. It's the same fundas, the equations may be different, but there's all kinds of physics which can be addressed using fluid mechanics. So my topic started with why study fluid mechanics, right? So like, do you want to vote for studying it or dropping it? One person thinks it should be studied. So what, guys, you want yes or no to fluid mechanics? Yes. Good. Thanks for your attention. Very beautiful question. So there is actually a mass. I didn't write it down because this flow is incompressible. So the correct equation goes like do rho by dou t plus del dot rho u equal to 0. Okay, and you can get this equation by taking a tiny box like this, some delta y, delta x, delta z, a tiny box, and you can say there is flow coming in, flow going out. You can write a little balance equation for this. So I will have rho times u coming in here, rho times u going out there, and so on. And if there's no mass creation inside that, I can write a balance equation for that, and that thing will give rise to this. Dou rho by dou t plus del dot rho u is equal to 0. So now imagine like there's a room with very few students in it, and I keep pushing more and more and more students inside. So my rho, the density, number density of students is going up, up and up, and nobody is leaving. That can happen. But if I've packed them full, I've packed them like a solid object, then if somebody comes in, somebody has to go out through the other door, correct? So my density inside, my number density inside cannot change. So then all changes in rho are cancelled out. So I'm left with del dot u is 0. So flow in is flow out, bus. So whenever it's incompressible, and so for water under all normal, I told you this holds for water in a swimming pool. In normal situations, this is correct. For water, some thick oil, things like that. For air also, surprisingly, it's correct whenever you have slow velocities. When you have a very fast velocity, like when the velocity of the air is similar to the velocity of sound, then you get compressibility effects that you can actually read about. It's not very difficult to do. Then that equation will come into effect. When you have high Mach number flows, like supersonic jet, things like that. So there'll be a shock wave, a compression wave, all interesting fluid dynamics will come over there. This situation? Very good question again. So like take pipe flow. Okay, I talked about pumping water from your sump to upstairs, right? You've got pipe flow. Iske andar, suppose I go at very slow velocities, then the velocity profile will look like this. It will not be turbulent. All those pastas and vortices will not be there. It will be going smoothly up. Okay, now I take this solution, I subject it to a stability analysis. I say instead of this velocity profile, if I got this velocity profile, will these perturbations die down or will they become turbulent? And if you do the simple analysis, you'll always get all e to the minus this, e to the minus that, e to the minus that. If you have 10,000 modes, all of them will decay. So then you will say, oh, it's going to be all laminar. But we know that's not true. Turbulence comes in the pipe. You cannot stop turbulence, even in, in your home situation. Yeah, so I'm just saying, like, take a pipe, you put some slow flow through it, and then you jump. Then it makes the velocity juggle around, right? That's all. So that little perturbation, or jump is a big one. You can do like very tiny things which will make it go to turbulence. It will always go to turbulence above a certain speed. There's nothing you can do to stop it. And so that's an example where transient growth did the job. No linear perturbation. Even if you made it quieter, you couldn't achieve laminar flow. And that's because transient growth takes the teeniest of perturbations and magnifies it by a factor of 10 to the 3 or something. And then it becomes a big perturbation, and then it becomes nonlinear. Okay, will you talk to me at tea time and ask questions? Yes? Okay, ask it now. Okay, thanks for your attention.